We are going to start the new chapter D and F block element. So our new chapter is D and F block element. As per NCERT textbook, it is of 8th chapter. Let's study what is given in D and F block elements. As you all know, in long form of periodic table or in modern periodic table, the elements of group number 3 to 12 are called D block elements. What are D block elements? Elements from group number 3 to 12 are called D block elements. Why these elements are called D block? If you write the electronic configuration of any one of the element present in this area, for example, if we consider scantium, scantium is one of the D block element, so whose atomic number is 21. If you write the electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6. When you write up to 3p6, 2 plus 2, 4, 4 plus 6, 10, 10 plus 2, 12, 12 plus 6, 18, 18 electrons over. Instead of writing this much, simply we can write by putting square organ in square bracket, it will be equal. So after completing 3p orbital, as per above principle, the next energy level is 4s orbital. The 4s orbital is completed. When 4s orbital is completed, now totally 20 electrons over. In the case of scantium, 21. One more electron is present. So after completing 4s orbital, as per above principle, 3d orbital will fill. So 3d orbital contains only one electron. So the last electron of these elements enter d orbital, but that d orbital is present as a penultimate shell. So what do you mean by penultimate shell? Last but one. From the last, the next orbital is called penultimate shell. So the elements which contain partially filled d orbital in the penultimate shell is called D block elements. The elements of group number 3 to 12 are called D block element because if we write the electronic configuration of this element, the last electron enters d orbital and also the d orbital is present as a penultimate shell. Penultimate shell means last but one. So the elements which possess partially filled d orbital is called D block element. But in this area, the elements of group 12, if you consider the elements of group 12 consists of zinc, cadmium, mercury. Zinc, cadmium, mercury. The atomic number of zinc is 30. If you write the electronic configuration of zinc, so if you write argon, that means 18 electron completed. After completing argon, 4s2, that is 18 plus 2, 20 electron overs. Then 3d orbital. 3d orbital contains 10 electrons. That means it contains completely filled d orbital. As per definition, the elements which possess partially filled d orbital in the penultimate shell is called D block elements. Then can you call this zinc as a d block elements? No. Why? Because they possess completely filled d orbital. The same case when we are writing the electronic configuration of cadmium as well as mercury. Cadmium contain, if you write 4d10 will come. Mercury contain 5d10. So the elements which contain completely filled d orbitals are not considered as d block elements. But we are studying zinc, cadmium, mercury. That means the elements of group 12 also along with the transition elements. Why? Because they are the nth member of the series. The chemistry of zinc, cadmium, mercury are included along with the d block elements only because they are the nth member of the series. Why zinc is not considered as a d block elements? Because they contain completely filled d orbital. As per definition, those elements which contain partially filled d orbital is called d block elements. But the chemistry of zinc, cadmium, mercury, that means group 12 elements are included along with the d block element. Only reason is they are the nth member of the series. If you write the electronic configuration of group 11 element, if you write the electronic configuration, so the group 11 consists of silver, gold, platinum. If you write the electronic configuration, the 11th group consists of copper, silver, gold. These are called coinage metals. So if you write the electronic configuration, they are also contain D10 configuration. They are also, if you write the electronic configuration of these elements, they are also possess D10 configuration. Then how can you consider that as a d block element? Because in their common oxidation state, they possess partially filled d orbital. So we are elaborating or expanding our definition. What are d block element? Those elements which contain partially filled d orbital in the penultimate shell, either in ground state or in common oxidation state. If an element possesses partially filled d orbital either in its oxidation state or in ground state as a penultimate shell, then it is called d block elements. If we are seeing the d block elements, they are situated between highly electropositive s block elements and highly electronegative p block elements. Therefore, these d block elements show some transition in their properties. Their properties are showing some transition from s block to p block. They are showing some transition from electropositive to electronegative. That is why d block elements are also known as transition elements. They are also known as transition elements because they are showing some transition in their properties from s block to p block elements. Since almost all the elements are metals, they are also often called transition metals. So d block elements are often called transition metals. So based on the d orbital where the last electron enters, we are having 4 series of d block elements: 3d series, 4d series, 5d series, 6d series. Like that we are having 4 series of transition methods. 3d series is otherwise called first row transition series, second row transition series, third row transition series, fourth row transition series. So we are having first row or 3d series, second row or 4d series, third row or 5d series, fourth row or 6d series. This 3d series starts with the scantium and ends with the zinc. There are totally 10 elements are present. So the second row transition series start with the ytterbium and end with the cadmium. The next row, that is the third row transition series, starts with the lanthanum and ends with the mercury. And the fourth row transition series start with the actinium and it is incomplete. It is incomplete. In third row and fourth row, there are 14 elements kept at the bottom as F block elements. They are called 4F block elements and 5F block elements, or otherwise called lanthanides and actinides. They are kept separately in the periodic table at the bottom. Electronic configuration. The general outermost electronic configuration of D block element is n-1 d raised to 1 to 10 and ns raised to 1, 2. This is the general outermost electronic configuration of D block element. This generalization having lot of exception. Why? The only reason behind in this is this n-1 d orbital and ns orbital having almost equal energy. That is, the energy difference between ns orbital and n-1 d orbital is very low. Because of that, there are a lot of exceptions are present in this consequence. For example, let us consider the electronic configuration of chromium of first row transition series. If you write the electronic configuration of chromium atomic number 24. So if you write the electronic configuration, argon, already we discussed, if you are writing argon in square bracket 18 electrons over, we know that after completing 3p orbital, 4s orbital will complete. That is 4s2. That is 20 electrons over. Chromium, what about the atomic number? 24. That means 4 more electrons wants to be filled. Where the 4 more electrons will go? It will automatically goes to d orbital. This is the theoretical electronic configuration of chromium. But actual electronic configuration of chromium is argon 3d5 4s1. This is the actual real electronic configuration of chromium. That means one electron is shifted from 4s orbital to 3d orbital. Normally shifting of electron from one orbital to another orbital is not possible. But here electron is shifted from one orbital to other orbital. For what? To maintain the stability. Because 3D contains 4 electrons. We all know if d orbital contains 5 electrons, it is half filled. 5 electron means half filled. Half filled state is a stable state. To maintain the stability, one electron is shifted from 4s to 5d. 4s to 3d. How is it possible? Because both these 3d and 4s orbital having almost same energy level. Since they are having a same energy level, to maintain stability, one electron is shifted from 4s orbital to 3d orbital. Therefore, the real actual electronic configuration of chromium is argon 3d5 4s1. The same case we can see in the case of copper also. If you write the electronic configuration of copper What about the atomic number of copper? Copper, atomic number 29. If you write the electronic configuration, if you are putting argon in square bracket, how many electrons completed? 18 electron completed. That means up to 3p orbital. After 3p orbital, which will be completing 4s orbital is completing, that is 4s2. 20 electrons over. Copper atomic number is 29. So 3d9. This is the theoretical electronic configuration of copper. But to maintain this energy level, to maintain the stability, one electron shifted from 3s to 3d orbital. So the actual electronic configuration of copper is organ 3d10 4s1. So general outermost electronic configuration of d block element is n-1 d orbital raised to 1 to 10 and ns raised to 1, 2. This is the general outermost electronic configuration of d block elements. But this generalization having lot of exceptions. Why the exception comes? Why? Because n-1 d orbital and ns orbital having almost equal energy. So we consider two examples. One is the electronic configuration of chromium. Another one the electronic configuration of copper. If you write the electronic configuration of first row transition series, listen here, first row transition series. First row transition series is otherwise called 3D series, which consists of scandium, titanium, vanadium, chromium, manganese, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. We are getting for scandium argon 3d1 4s2. If you write the electronic configuration of titanium, atomic number become 22. So we are getting argon 3d2 4s2. So if we come to the next one, vanadium 3d3 4s2. If you come to manganese 3d5 4s1, it will goes like this. That means when we move from left to right in the d block area, the number of electrons present in the outermost orbital is same. If you write the electronic configuration of first group elements, lithium, sodium, potassium, rubidium, cesium, all these elements possess only one electrons in their outermost orbital. That means they are having same number of electrons in the outermost orbital. Number of electrons in the outermost orbital is same, then they are showing same characteristic features. Like that, if we are writing the electronic configuration of first row transition series, all these elements possess almost same number of electrons in the outermost orbital. That is why when we are moving from left to right, their properties also be identical. That is why in D block area, we are studying the properties in series. In all the other cases, we studied group wise. We studied about 16th group, 17th group, 18th group, like that we studied. But in D block area, we are studying the properties in series. Why? Because when we move from left to right, the number of electrons present in the valence shell or the outermost orbital is same. When the number of electron is same, automatically they are showing same characteristic features. That is why we are studying the properties in series, not in group. Of course, when we are moving from top to bottom, also they are having some identical properties, but that identity having lot of discrepancies. Why? because of the lanthanide contraction and actinide contraction, which we are going to study later. Almost all the D block elements are metals. They are showing metallic properties such as malleability, ductility, high thermal and electrical conductivity. Almost all the elements are showing this. Almost all the elements are hard. Why they are showing metallic property? Because both n-1 d orbital and ns orbitals are involved in bonding. When number of unpaired electron in n-1 d orbital is increasing, their metallic property also increases. For example, if you consider zinc, cadmium, mercury, they are having very low, no unpaired electrons are present in the case of zinc, cadmium, mercury. So they are soft. When we are comparing with the other elements of D block area, zinc, cadmium, mercury are soft. Why? They are showing low, what we call low metallic character. Why? Due to the absence of unpaired electrons in n-1 d orbitals. Since almost all the elements in D block area is metals, they are showing high melting and boiling point. All the D block elements except zinc, cadmium, mercury possess high melting and boiling point. Why? Because the melting and boiling point depends on the metallic property or depends on the metallic bond. The metallic bond in turns depends on number of unpaired electrons. When number of unpaired electron is more, automatically the strength of metallic bonding is more. When we are moving from left to right, that means when we are moving from scantium consists of only one unpaired electron in the d orbital. If you consider the electronic configuration, you can easily understand. So when we are moving from left to right, scantium to titanium, number of unpaired electron is increasing, so melting point is also increases, that is, listen here, scantium, titanium, vanadium, it increases. For manganese it decreases. Then again for iron it slightly increases, then it will gradually decrease. This is the variation of melting point of the D block element, first row transition series. In the case of first row transition series, manganese possesses low melting and boiling point. Why? Because it consists of D5 configuration. That means it consists of n-1 D5 NS2 configuration. That is stable electronic configuration. Due to the stable electronic configuration, their electrons are highly bound by nucleus and they are not involved in bonding. Therefore, it possesses low melting and boiling point. The same case or the same reason we can apply in the case of technetium, which is the middle element of second row transition series. What about melting and boiling point? When we move from left to right, it gradually increases. Why? Because of the number of unpaired electron is increasing. It increases up to middle, but the middle element manganese possesses low melting and boiling point. Why? Due to stable electronic configuration. Then after manganese, number of unpaired electrons decreases gradually. Automatically the melting and boiling point is also decreases. That's all about the melting and boiling point.